Yeah, hello. So we are this time, and happy to see you there, and happy also to see you working on your project. And yeah, so I realized this week project is more about statistics, about inferential statistics, and especially about Bayesian statistics. So we used to deal with frequentist statistic, like yeah, with like we know it as the classic one, but this time Bayesian statistic is another school, and so there are some differences between the frequentist approach and the Bayesian approach. And since yesterday, you guys have been already introduced by Jonas and by Yebebal also. So introduce in terms of get introduction, a quick introduction on the paper. So at this time you should have read the methodology and the main result they found in the paper, and you should realize that there is a lot of Bayesian statistics, and that's what Yabi was talking about yesterday also. Yeah, in terms of probability thinking. Yeah, so what I want to do is to make a short tutorial about the concept behind the Bayesian statistics. So, like when we are dealing with Bayesian statistics, we should be considering some things like probability distribution. Yeah, and then there are new concepts like likelihood, like the prior distribution, the posterior probability. So those things may seem like new things to you. So I wanted to get you on board, like yes, let's get some understanding about the concept. Yeah, about the concept behind, and so that you understand the things and the main difference from this with the frequentist approach. So that's why for this tutorial I want there is no Jupyter notebook. I just want to go through Kaggle because I find a very useful tutorial uh, which can help you a lot. So me or Sebastian will share it in the Slack channel as well. Yeah, and even here I will share it right now so that you can have access. So like you will just we are just going to yeah, yeah, so we are just going to into Kaggle right now, go for the tutorial so that we get introduced to the concepts I want you to know. So this is the tutorial introduction to Bayesian inference. Yeah, so as I told you, there is statistical inference, there is the classical statistical inference, and there is Bayesian inference. Yeah, so inference is like you already know that, like I have some data, and I have a population. So I have the population, and from the population I have some sample of data, and I want to make some conclusion. Yeah, I want to make some conclusion or some statements about the entire population. Yeah, so I will have to estimate some parameters. Yeah, so the parameters I will estimate, I will use a statistical model to estimate those parameters. Or yeah, I can do point estimates estimation for a confidence interval. So like I will use just some sample of data to make my estimation. So I can for example estimate the average age of 10 academy junior data scientist. Yeah, so let's say I will just collect data about, so I know you are not a lot, so this is just an example. If I have a huge population, like about 10,000 or yeah, 10 yeah million thousand, like I will just find a methodology to sample, and there are methodology for that to sample my data, and from there I will just estimate my parameters. So the parameters I could want could just be the age or the tire, or I don't know, whatever you want, or the average grades, yeah, points, or like yeah, just estimate everything you want. So the average point in SQL, the average point in, so is depend on what I want to estimate. So it's depend on the parameter. So now this, to do this estimation, we can go for the classical approach. So the classical approach, so in general, it's like the process of determining the properties of a model. Yeah, a model or a distribution given some data. Yeah, so let's say for example I have Lawal, and then I have some other people with the average mark, yeah, tiled now. So let's refer for example to the leaderboard, and you have each person and his mark tiled now, and then you want to know to which distribution the data fit the best. Yeah, so like which distribution can fit the data the best. Yeah, so there are a lot of distribution in statistics, and depending on your the phenomena you want to actually model, you will actually choose your distribution. Yeah, so if you want to for example, let's say I have the distribution, I have the data points about the average mark of every student here, and I want to know which distribution will fit this the best. So there are a lot of distribution. There are binomial distribution, there are a Poisson distribution, there are exponential distribution, there are normal distribution. Yeah, so there are gamma, beta, and so like there are a lot of distribution. And now I wanted to I wanted you to first time know what is each distribution. How can we, when to use each distribution? So like when we take for example the binomial distribution or the Bernoulli distribution. Yeah, what when can we use such distribution? And so in the classical approach, if we know we have some sample of data, we will just adjust. Yeah, we'll just fit those distribution. There are statistical tests for that to know if a distribution fits some data or not. So there are the quick key square, yeah, the key square testing, so which will help us to know that yeah, this distribution actually fit this data. So once you know that this distribution fit this data, you will just later use the distribution to actually compute the probability of an event to happen using the data. Yeah, so that's why distribution are important. So depending on the phenomena you are actually modeling, you will actually need to specify your distribution. Yeah, so if you are using binomial distribution, there are some assumption. If you are using Poisson distribution, yeah, the variable you should be modeling should for example be like a discrete variable, a discrete like a count data variable. Yeah, let's say for example the number of call made during a day. Yeah, so like is a number of call is a discrete variable. So basically this distribution should be modeled using like Poisson distribution. So if you say for example, yeah, if I will, I want to know the number of, let's say the number of if I run an exam, I have to fail or succeed. So the probability to get k sources, for example, this the random variable describing this experience will just follow a normal a binomial distribution. So like there are some basic things you should know about the distribution, and I wanted to you to know that before. But once you know about the distribution, I will share a link about the distribution. Poisson binomial normal distribution. Normal distribution fits let's say all kind of data with certain criterion. Yeah, so because if a random variable just is following actually Poisson or binomial distribution, there are some assumptions, you can actually check, and if they match, you can just consider the variable is also following normal distribution. So the normal distribution is like, yeah, then as the name indicate, the normal situation. At the beginning you have field density, lower density, and then in the middle you have a concentrated density, and then by the end you have a low density also. Yeah, so okay, so apart from this, so I was talking about the general modeling, the general statistical inference, like the classical, the frequencies approach, and versus the Bayesian approach. So in the frequencies approach, they will just determine the property of the model. So if I want a model, the model could just be a binomial model, a binomial distribution. Yeah, so the property of the model is actually the parameter of the model. Yeah, so we are going to use the data to actually estimate the parameter. Yeah, so like I want to compute some probability, but before I need the parameter, so I will use this parameter later to compute some probability from the data. So now in Bayesian inference, yeah, in Bayesian inference, there are some difference. Yeah, so where is the difference? Yeah, the difference is about the parameter, because when the frequent approach consider the parameters as true and constant, the Bayesian approach will actually treat the model parameters as a random variable, and usually want to deduce probability statement about the distribution of parameters. So you saw that yesterday, but it's like, let's say, if we are dealing with a binomial distribution, for example, the parameter of this model is actually the p and the n. So if it's bandwidth distribution, the parameter is just the p. So like we want to estimate, we want to make some statement about the parameters, the distribution of the parameters. So the distribution of the parameter, we know that the p is always between the 0 and 1, but we want to make some assumption, some statement about, yeah, where is the true p, where is the value of the p, and what are some statistical statement we can make to characterize the distribution of the p. Yeah, so using a frequencies approach, we just know that the p is a constant which we can estimate from the data. But actually using Bayesian, the p is just considered like another variable which follow a distribution and depending on the prior probability. So there are some notion I wanted to introduce all of them here. So know that Bayesian inference use the famous Bayes rule. So the Bayes rule is more likely based on conditional probability. So probability of A knowing B is equal to blah blah. So you know the formula. So what is important here is like translating this formula into a real problem. Like from this formula, from this conditional probability formula, how can we actually derive the notion of prior probability, of posterior probability, of likelihood? Yeah. So like for model-based inference, we can replace A with the parameter theta and p. Yeah, so it's dependent. So, but I think translating this formula in the modeling thing, like the probability of A knowing B is just like a formula showing the things in terms of statement. Like I have an event E and another event B. So if I want to determine the probability of the event E, knowing the event B, then I will use the formula probability of A B knowing A multiplied it by, and so you saw the properties of the probability function yesterday. So you have the multiplication, you have the sum, and you have the division, you have everything. So like translating now this formula into the modeling part, you will just have the notion of prior probability, posterior probability, and likelihood. Like what? Like the A could just be become your parameters. Like you want to model, you want to give some statement, you want to know the distribution of your parameters, of your model parameters, knowing the data and the prior. Yeah. So knowing the data and the prior, so the probability of A knowing B will just be the probability of data knowing I. Like, yeah, if I know the prior, if I have some prior information, yeah, how could I derive the probability of my parameters? Like, I have the data and I have the prior, then I want the probability of data. So, like knowing those two information. So this is just called the posterior probability. So the probability of A knowing B will just be the posterior probability, and then there will be the likelihood and the prior. So the prior is just about the parameters. Yes. So the previous information we have about the parameters. So yesterday you was discussing about running in the year. So there are a lot of the in the year there are so 365 days in a year. So what is actually the if we want to estimate, yeah, if we want to estimate the probability of running, yeah, then we should have some prior information. So the prior information, yeah, we can just say it could just run any day in the year. So the probability, the prior probability of running is just 1 over 365. Yeah, and just close it like, yeah, we know the prior probability. And then how much did you how much run how many day of run do we have last year, for example, over the year? Like if we want, we can say just 10 or just 100 or just like 3 months, so like 30 days. So and from there we can estimate the likelihood. So what happened with the data is actually the likelihood, and what we know about the parameter we want to estimate before is actually the prior. And using the prior and the likelihood, we will actually get the posterior. So the posterior is just some kind of notion like proportional to the likelihood and the prior probability. Yeah, so it's just like some notion, some name given to some statement. Like, so if you take the bias rule, it's very simple to understand. But if we translate now the bias rule into the modeling part, and then it's becoming more complex as we are changing the names, but it's nothing complex. Like we are just changing the name. The probability of A knowing B is just the posterior, and the probability of A is the prior. So what is the prior information we have about what is our ticket of belief about the parameter A before we use the data to estimate? So this is just the prior, and then so you should know three things. We have the posterior, we have the likelihood, and we have the prior. So, like the posterior probability is just proportional to the likelihood and the prior. So always think like that. Yeah. So what is our target in Bayesian statistic? It is the posterior. So we are going to use the likelihood and the prior to define the posterior. Yeah. So now this is an example about the coin flip. Like for better understanding of Bayesian style, yeah, you have a reference. So now we are observing whether a coin flip result in head or tails. So like we are not sure whether the coins at interest is fair or whether it might be biased due to some aspect of like similar things. So any bias may be related, so that we don't know the exact value of the p. Like we want to flip the coin, but at a frequencies level, we can imagine that we used to say we don't have any bias, so that we know directly that the p is constant and equal to zero point 0.5, like 50%. But here with Bayesian statistic, for any reason, we don't really know if the coin is biased or not. So we don't know, and we want to make some inference. We want to make know the distribution of the p. As we don't know any information about the p, we don't know if the p will be 50% or not. We have to infer about the distribution of the p. So this is the main objective of the Bayesian statistics. So here, yeah, so thus we want to conduct a statistical inference on the parameter p, which will describe the probability of flipping head. So by using the Bayesian framework. Yeah. So the probability of flipping ties is just 1 minus p, because if we know the probability of flipping head, then we should know the probability of flipping a ties, which is the contrary. Like the sum of the probability should always be 1. Yeah. So now we consider a set of observation d by flipping the coin several times. So then we have data. Yeah. So we have data and we have the parameter p. So what derive is like we have the data and we have the parameter p. So we want to infer about the distribution of the parameter p, knowing the data and the prior information we have about the parameter p. So the prior information is our degree of belief. So like if we want to flip the coin, we could just say, yeah, me, I believe that the coin is making a such way that we have more chance to get like the head than the thighs. And someone will just come and say, no, me, I have my degree of belief in such that I think that we will have more probability to get thighs than head. So, and some other people will just say, oh, me, I think that the coin is not biased. Like we have 50% of chance. So like the value of p is becoming like several, and we want to know, to make some assumption. We want to know the distribution of the real value of p. So that's why we call Bayesian framework. Like we don't know exactly what is the value of p. Somebody could just say the value of p is 0.4, and some other people will say it's no, it's 0.8, and some other people will say it's like 50%. So how do we actually know the real value of p, or at least the distribution of p? So if we know the distribution of p, we will choose as p the value for which we have the higher probability density. So this is the advantage of the distribution. So like if you know the distribution, you are just gonna choose the value for which you have the higher probability density. So here we want to use two things. We want to use the data, and we want to use our prior information, our prior knowledge about the parameters p. Yeah. So here we have consider a set of observation d, and we consider also the parameters p. And then I told you that the posterior probability, yeah, is the probability of p knowing the data. So like is actually proportional to the probability of data knowing p, which is the likelihood, and multiplied it by the probability of P, like the prior probability of P. So before we don't know the data, we have some thinking about what could be the real value of P coming from our degree of belief. Like, yeah, I believe that this value of P could just be between this, or could just be this punctual value. But now, knowing the data, making the experience, the binomial experience, flipping coin and getting results, make us change our opinion. So the opinion is the updated opinion. So from the prior and for the data, we get an updated opinion. So the updated opinion is actually the posterior probability. So this is what we want. So the model is actually the binomial distribution. So which is a discrete probability distribution for the number of sources in a sequence of n independent binary experiments. Like we want to estimate the P. So which model can actually be used to estimate the P? Yeah. So which kind of experiment we can actually use to estimate the P? So the P is the probability of getting the head. Yeah, so we want to flip the coin. So if we are looking for probability of getting the head, look at the P as the frequentist approach of doing that. So I want to estimate at what is the percentage of head I could get when running an experience like that. So I will just make the experience and collect the data. From there, I will get the frequency. So I will use the data to estimate the value of P to fit the model, like using a chi-square adequation test, a chi-square adequation test. I will just get the parameters P, like P. Yeah, I will get the parameters P, and from P I can just compute now the probability to get 2 times the head, K times the head, and whatever I want. But using the data, using my experience, I will get the data, and using the data I will get the model parameter. Yeah, so now this is what is happening exactly here, but because we have the P and we have the experience, and we know that in order to estimate P, we have to run a binomial experience. Yeah, so the model here, the likelihood model, is gonna be a binomial distribution model. So which is a discrete probability distribution of number of for the number of sources in a sequence of n independent. So n independent will be like the number of trial, like the total number of possibility we actually have. So we are running a binary experiment, so coin flip resulting in head or tails. So like the binomial distribution is conditioned by the parameter n, so the number of trial, and the P, which is the probability of flipping head, and this P is what we are looking for. So the probability mass function of the binomial distribution, we know that. So this probability mass function of the distribution we need to fit the model of likelihood is actually used as likelihood. So the likelihood function I was just talking about here using the data is just about the probability distribution, the probability mass function of the distribution which will fit better with the P value. So like here we are using a binomial distribution. So it's like we already know the value of the likelihood, like the expression, at least the expression of the likelihood. Then we need to set the expression of the prior probability. How can we actually compute the prior probability? So we know how to calculate the likelihood based on the probability mass function, right? So like of binomial distribution, because this binomial distribution seems to be the better distribution to actually get our P. Yeah, knowing the data, like, so But how can we actually use the prior? So as mentioned, the prior is our belief in the parameter before observing the data. So we want to make the experience to confirm or not. It's like an hypothesis testing. So I have a prior belief. I believe that this parameter is gonna like I believe that 100% of 10 academic fellow are just gonna complete the project the project and get a job by the end of the program. So I want to test that. So this is my prior belief. But my prior belief is so about a parameters here. So the parameter is actually the rate of success in the project and getting the job. So this is a prior belief because I didn't base on the data. I have a feeling like our selection process was very hard. People are very engaged, and I think, yeah, they are just going to make amazing things and get job ready by the end, and then they will success and they will get job. So, but now I want to collect some information like, yeah, each time we are doing leaderboard, we are giving assignment and people are just doing, and we are grading, and we have 12 week, and from each week they are gonna have some grads, and from all those grads and from their contribution and from everything, we are just gonna have a posterior distribution of the parameters. So the parameters here is this the success rate. Yeah, so it's exactly like that. So if I have the likelihood now, how can I actually choose the prior? So the prior is our belief in the parameters. So but yeah, so basically we can express our assumption about the parameter p in our model in terms of a nodal probability distribution. Yeah, so the likelihood is actually a probability distribution, but more concentrate on the data. But the belief, the prior belief is another probability distribution. Yeah, so our belief, our degree of belief will just follow a distribution. So how can we actually find this distribution? So this is another question. So there are some scientific work, there are some demonstrations. So all those things are just mathematics, and there have been some investigation already, and there have been some demonstration, and they found that some mathematicians already found that when you have this likelihood, yeah, you are just is like the prior should more likely be this probability distribution, or yeah, this function. And when you have this prior and this likelihood, you are just gonna have this this family of posterior. Things have been done here for also like we know today that if my prior follow binomial distribution, then my what do I say? My prior no, my likelihood. If I know that my likelihood follow this binomial distribution, my prior is just going to follow this distribution, and from the above distribution, my posterior is will be belong a family of distribution too. So in case I will share this with you too. I wanted to. So this is an Excel sheet, so where I actually make it like if you know your likelihood and you know the model parameter you want to, so you don't need the model parameter, but from the likelihood you will directly know the model parameters. So based on the likelihood, what will be your conjugate prior distribution? Yeah, so there are some association, some couples, like if you have a prior, if you have a likelihood, you will have a prior, and from this prior and the likelihood, you just have a posterior. So it's like more likely like a demonstration of a mathematical formula. Like if I have a binomial distribution, I know the probability mass function of the binomial distribution. So it's about P of S equal to K will be equal to the combination of X like So you know the formula. So the combination of k in n element multiplied it by the probability of success, like p exponent k multiplied it by 1 minus p exponent n minus k. So like if you have this probability mass distribution function, and you also have the beta probability distribution function, you will just like multiply those two functions, and at the end you will see the family of the distribution you are just gonna have. In this case, if you have Bernoulli distribution, the conjugate prior is in the family of beta, and the binomial, for the binomial distribution also, the conjugate prior should be in beta family. And when you have a conjugate prior in beta family, I didn't put that here, but you can find it on internet. The conjugate posterior, the posterior distribution is also belong to beta family. So actually, the distribution have some characteristics, like some properties. So I think you will Google about that, and we will also share some resources about the distribution. Like if I want to use binomial, for example, I make sure that yes, I have an experience, a binary experience, and I'm about computing the number, the probability of getting k uh, times of these results based on a total number of results. So I'm using binomial. So like if I want to predict to get the probability of getting like a random variable b, like a k, and k is like just a discrete value. So this is more likely related to Poisson distribution. But if I want to get a continuous distribution, so there are normal distribution for that. Or if I'm modeling, for example, let's say the survival rate of bacteria, or survival rate, let's say the coronavirus. So you will see that you have some kind of exponential model. So like there is exponential distribution. So the exponential distribution will just run quickly, and then we have some asymptotic behavior at the head. Yeah. So when it's reach some level, it's becoming asymptotic, like you have some asymptotic behavior. So depending on the phenomena you want to model, you will actually need to fit some distribution, and from those distribution you will get your parameters. So this parameter will be the things you will actually compute using posterior probability, and with your prior knowledge about the parameters. So in this case, if we want to know the distribution of 10 academy fellows, like the success rate, the distribution of the success rate at the end of the program, yeah, this is a rate. So the better distribution to actually fit rate, like rate are value like in one, in between 0 and 1, like in a continuous bound of 0 and 1. So it could be 0.2, 0.2.2, like so continuous value. So but the biggest value is 1 and the lowest is 0. So if you have value like that, if you have random variables like that, like the p in this case, like yeah, the probability of getting a head, so it's actually a rate failing in that interval, like this continuous interval. So the better distribution to actually model a weight value like those is like a beta distribution. So the beta distribution is for proportion. So actually the probability of getting a head is actually a proportion. So if I want to model that, I will use beta distribution. So it's better to have a beta distribution thinking as prior. Yeah, so that's why they make it like that. So now, if I'm looking for another kind of parameter like the mean, so if I'm using normal distribution and I'm looking for the mean, yeah, so the mean will actually is not actually belonging to one to zero for from 0 to 1 as a continuous interval, but another, so it's like a value, a continuous value too. So continuous value will be just model using normal distribution. So the likelihood will be normal, and the prior will be normal, and then the posterior will be also normal. So the posterior, you don't have to worry about that, because the most important things are the likelihood and the prior. If you know the likelihood from the kind of experience you want to conduct and from the parameter you want to estimate, so using the data, you know the likelihood, and using your degree of belief, you will know the prior. So like the prior is depend on the parameter you want to estimate. So if the parameter is like falling in a continuous interval with no limit, then you can just use a normal distribution. Or if it's like belonging to a limited continuous, like in this case 0 to 1, then it's like a proportion, and the better distribution actually for proportion is the beta distribution. So that's why here they say that as we already know the likelihood as binomial, so the parameters here is a proportion. And as the parameter is a proportion, the prior distribution, the prior knowledge should be related to proportion. And here, the better below all the distribution we know, the better distribution to actually fit proportion is the beta distribution. So that's why the prior will be a beta distribution. So once you know the prior, you will just multiply the prior by the likelihood to get the posterior. So these are mathematical function, like you can try using a paper and a bit of paper and a pen, like just you just take your computer, open some notebook and try some demonstration. You will get that, yeah, it's you can also check on internet because it's available. We are not I'm not going deep in the mathematical demonstration, but once you multiply the probability mass function of a binomial distribution and the probability mass function of a beta distribution, you will surely get a beta distribution at the end. So the parameter of the beta distribution at the end will just be different from the parameter of the prior beta distribution, so that your information about the distribution at the posterior level will just be different from what you get at the prior level, because now you have the data inside. Yeah. So so that was explaining everything. So the beta distribution is a continuous probability distribution over the interval 0, 1. So the probability distribution function of beta distribution is defined as, so you have the probability distribution of beta here, and so I think this distribution is just like, so from here you have hyperparameters. So the prior probability mass function distribution parameter are just called the hyperparameters of our model. Like, yeah, we they are not considered like as random. We have to choose them manually, and then from those value we choose as constant, we'll get some distribution about the parameters we want to estimate. So they are called hyperparameters. Like, they are the parameters we can actually choose ourselves. So we call parameter we can actually choose ourselves. So like if you are running machine learning random forest decision, so random forest, you have the number of tree decision forest, you have the number of branch, the number of nodes. So it's depend on what you want to do. So here the alpha and the beta are our value for the hyperparameters. So the value we can actually fit choose to actually reflect our degree of belief. Yeah. So if you actually set this value to 1, like alpha equal to 1 and beta equal to 1, it's just become a uniform distribution. That like it will just take only one value. It's like the beta the so you have gamma function here. So gamma of alpha plus beta divided by gamma of alpha plus gamma of beta. So this is just like gamma is also a function. So it's also a function, and this function gamma we may introduce factorial things if I remember well. But whatever you I mean, this function, when you take the value, the expression of this function, and you integrate with the input like alpha plus beta or alpha and beta in the denominator, you will just, if you replace alpha and beta by 1 and 1, you will get some uniform distribution, like a constant distribution as the probability mass function. So it's depend on, if you choose some other value, you will get another distribution. So it's really depend on the value of alpha and beta. So our degree of belief as prior will depend on the hyperparameters, which are alpha and beta. So if I choose alpha and beta to be symmetric, if I choose alpha and beta to be symmetric, then I will get like a 50 chance to about a 50 distribution chance about the parameter piece, like second a 50% chance to for the parameter to be below, like below 0.5, and 50% to be above 0.5. So the parameter will have more concentrated distribution, more high level the high value of the density function will be obtained closely to the value 0.5. So depending on the value I choose for the beta distribution, I advise you to read about beta distribution later, because it's very important if you want to model the parameters, the proportion. And so depending, but here they show some things like, so here they are saying alpha and beta are positive shape parameter controlling the shape of the distribution. So the shape of the distribution will directly affect our degree of belief. So like if the shape is like flat or like, so it's depend. If it's symmetric, actually, then we will get like 50-50%. Then we believe in the 50-50. But if too flat, like, yeah. So if it's too plan or too flat, we will just we can just interpret it like we don't have any any useful information about the parameter p. Like the parameter, we think that the parameter is just like the probability, the density function of the parameter is just constant over all the value of the parameter. So if we say what is the probability for our p to be 0, yeah, the probability is the same as if we say what is our probability of p to be 0.7, or if we want to say what is the probability of our p to be a 1. So like this is the units, the how to say, the uniform distribution. So that's why I say, yeah, if we get alpha equal to beta equal to 1, then we will get like a flat distribution. So that, yeah, we don't, it's the interpretation is just, we don't have any information about the prior. We don't know anything. We don't know. We like, yeah, we just want to base on the data and estimate the posterior. We don't know anything. It's like planning. Yeah. So yeah, I don't want to go in the coding part for now. I know that you have a lot of code, but I want to make sure you understand the concept. So here, so they are trying the coding. It's not in important. They are just like sampling the, so specifying the prior. Yeah, they are specifying the prior probability density, like playing around the value of hyperparameters. I told you alpha and beta. So here they want to consider a symmetric distribution. Like, yeah, we think that we have 50-50. Like the p could just be 0.5, like 50% to be left and 50% of things to be right. So like alpha equal to beta equal to 10, and once they do that, they get the plot. Like you can actually realize we have the higher probability density value around the half value, around the 0.5. Yeah. So actually, so look at the value of the probability density. So 3.5. So the probability density, I want to tell you something. The probability density is actually is not the probability. The probability have some characteristic, like always falling in between 0 and 1. So here actually just realize the density is actually over 1. So this is not the probability, this is the probability density. So to get the probability, you have to multiply the density of the probability with the probability element, like the observation. So this observation here, like the 0.2 multiplied by this, yeah. So like this is not actually the probability value, but it's actually the density. So what I want to realize you to realize here is that if we shape our our hyperparameters to be like symmetric, so alpha equal to 10 and beta equal to 10, then we get a lot of like the highest value of density around the 0.5. Like we set it like symmetric. So this is how to express our degree of belief. So we believe that if we set that as there, so this depend on everyone. Like, yeah, you can just say I think that. So for the rates of success of 10 academy fellows, I'm talking about, like, it's better to actually make not asymmetric things, like, yeah, pushing the probability, the parameter p toward the one. Yeah. So I was just like, so it was a joking. So like you have the highest value of probability mass function around the 0.5 here. Yeah. So now realize this value is actually 3.5. And once we decide to increase the value of alpha, so alpha and beta, we increase them to hundreds and see what we get. We have more than 3.5 as probability density function around the half value of p. Yeah. So the more alpha and beta are greater, the more the highest the density function mass is. So like yeah. So if we want to increase the probability to get our p-fall in this interval, then we have to play on the alpha and beta, which are actually the hyperparameters. Yeah. So they are doing same things here. They are increasing to 1,000. Yeah. So once you get your, so here, yeah, still this is what I want for 10 Academy. Like I want the PB, like, yeah, push it to what they want. So we get 100% of success. Yeah. And I want my family be placed in job, and then we make good relationship for future collaboration. Okay, so like this is so about the prior, yeah. And so this is what I was talking about, the uniform distribution. This is like we don't know anything about the parameter p. We don't know anything, like, yeah, alpha equal to 1 and beta equal to 1 make the beta distribution just because a uniform distribution. And uniform distribution is like constant over the interval from 0 to 1, only one value. So the value actually is like b minus a divided by what we say, b minus a divided by n, or divided by b, I think. So I didn't remember. It's like divided by b, but yeah, it's divided by the length of the interval, but I don't know. So it's like you will check it online, but the uniform distribution is just constant over all the value of p. Yeah, and the value here are there, and you can see that, yeah, we have a constant distribution. Yeah, so once you do all that, you can actually define your posterior. Yeah, so the posterior is nothing like, yeah, you will just you will just now play around the hyperparameters and the data to get now the posterior. So how can you, I show you how to play on the hyperparameter by modifying the value. You can actually change it from a symmetric prior, like in a bias prior, like in a constant prior. Yeah, as you don't know any information about that, so you can patch the p in the right side, or you can patch it in the left side, or you can just maintain it as constant. And now how to play on the data, yeah, using the sampling, like the value of k, the number of sample you want to make actually from the data will just make some precision about the posterior probability. So here this is what they are describing. So it's like the proportion, the posterior is just proportional to the likelihood and the prior. So it's a multiplication. So I already told you, if we have a binomial likelihood and a beta prior, we will have a beta posterior. So you have the table, but you will I advise you to search that online, because we have a more complex information. Because here I just have a discrete distribution function, but you have a lot more. So like normal distribution, geometry, so geometric is here, so log normal distribution. So there are a lot of other distribution you can actually get. So I advise you to check online and share by yourself in the Slack channel. I wanted to see, and looking forward to see the first person who will share that. Sebastian, have a look on that, and we will just okay. So like, apart from the posterior distribution, yeah, so I don't want it to go in the code right now. I know you have the code. I want to make sure you understand the concept, because if you understand the concept, then it's become more easier to you to address the coding parts. So I want to make, and also for for today submission about interim solution, I think all the question, we don't have a question about coding, or did I guess that? I think more questions are related to your understanding about the methodology, and yeah. So read the paper and get familiar, answer question, and that's will make it, I think. So this is the posterior, yeah. So the posterior density, probability density. So here, so we can see that with an increasing amount of random sample from the binomial distribution started with an initial uniform, yeah, so flat distribution, we increasingly believe in the true parameter p equal to, yeah. So like, I will give you this link, and you can actually see that, yeah. Yeah, so the p will not go over 0.4, because we specify that here before we start the experience computing the posterior. So we want our p be like 0.4, and we are just manipulating the sample of data, like, yeah, the key, and also the alpha, the hyperparameters. So we manipulate two things: the data and the degree of belief, the prior degree of belief. So the hyperparameters alpha and beta, and then the key. And as the key increase, we get just like the key or the n, like so the data, like the number of sample, so the n. So as the n increase, actually we just get like the true value, we just get closer to the true value of p. So before we run the things, they explain just at the above here, that they choose p to be actually 0.4, and then they try to model about the posterior to get the, so they try to act on the hyperparameters and the data, like the number of samples. So the number of samples will just accurate your model. So this is no, if you increase the number of sample, if you increase your data size, you will just accurate your model. So it's like what they are doing, like, so it's the prior was like very poor in terms of information, and now they are just increasing the number of n, and then from there they are just the true value of p, yeah. So at the beginning you will see that the prior was very poor, like very flat, and yeah, so you can see we have the density is just moving, the high density part is just moving toward the true value of p. So here, yeah, they are doing the same in the right side. So like, they are just passing, like, yeah. So the prior was very okay. So I advise you to read about that one. And yeah, so they are credible interval. Credible interval are just like the interval of the true value